All right, so this morning we're going to talk about the average value of a function and the second fundamental theorem of calculus. So the first thing that we need to talk about is the average value of a function, which they also sometimes refer to as the mean value theorem. Mean value theorem, okay? Because mean, again, just means average, and you learned that a long time ago, right? So mean just means average. So the average value of a function, okay? So let's figure out if we can see where this function derives from. So here's this curve, and it's actually the curve of x squared plus 1 because it's just a parabola, right? So we figured out when we were doing definite integrals in the last chapter that we could find the area. I don't really know why this graph goes over to 2 like that, but the integral of the area, the integral of the function from 0 to 2, and that would tell me the area, right? So the area, this area of this function right here, could be represented by the integral from a to b of f of x dx, which in this particular situation would be the integral from 0 to 2 of whatever this function is, right? Okay, so whatever it is from 0 to 2. But you could represent it generically like this, right? That's the area underneath this curve, okay? So we said, okay, we know how to do that, and we know how to approximate the area, right? If we find some sort of Riemann sum, so if we do the left-hand rectangle, that's going to underestimate. If we do the right-hand Riemann, and we just do one rectangle, that's going to overestimate. But somewhere on this curve between A and B, there has to be some rectangle that's going to equal the area under this curve, okay? So what we could do is we could maybe like lop off a piece of it right here and take this piece and like flatten it out and put it over here so that this piece becomes flat, which is what they've done in this image down here, okay? So if you'll look at this rectangle represents the average value or the average area underneath this curve, okay? So it's the same area, we've just converted it into a rectangle. So this same area, we've lopped off the top of this, flattened it out, and made it into its own rectangle, okay? So this distance right here is whatever f of c is, okay? So this point is c, right? The x value here is c. So whatever point is going to give me that average. So the height of my rectangle is f of c, okay? The distance from here to here, in this case, is the distance from 2 to 0, but typically the distance between these 2 points is the distance from B to A. So this distance would be B minus A, whatever that is, the distance between B and A, okay? So like if it was here and it was 1, that'd be 2 minus 1. If it was a 0.5, it'd be 2 minus 0.5. Here it's 2 to 0, so we're good. So the area of this rectangle, we could say is the height, okay, times the width, which is B minus A. And the whole point of the mean value theorem is that the area of this rectangle is supposed to equal the area underneath this curve, right? So we could set this equal to the integral, right? So this integral should equal the area of this rectangle, okay? So the area here should equal the area of this rectangle, okay? So what is happening is it's giving us this point C, okay? Well, if the area underneath here is the same as the area underneath here, then this has to be the average height of your function, okay? So what that's going to do in terms of physics and things like that is this is going to give us, say, the average velocity of a function. It's going to give us the average position of a function. Or just in generic math terms, it's going to give us the average height of a function, okay? So that's what we're looking for when we're doing this. So if you look down here, the mean value theorem for integrals, they wrote it down. If f is continuous on the closed interval from a to b, then there's got to be some number c, so some x value, where the integral is equal to the average area of the rectangle, okay? So what this says is the base of the rectangle, b minus a, times the height of the rectangle at some point, all right? they actually rewrite this formula so it's a little nicer to use. I've never seen it written like this. So the way we're going to write it, because what they normally do is they say, okay, so if you've got the integral from a to b of the function equals the area of the average height times the width at the average height, right? Times the width of the rectangle. If this piece right here, f of c, represents the average height, then if we divide by this, we've solved for the average height. So what they normally do, and the way that I've always seen it written that makes more sense to me, if you divide by b minus a, that gives you this coefficient in the front, because we divided by b minus a, and then you leave the integral alone in the back. So you would say the average value of the function is equal to 1 over b minus a, so 1 over the two endpoints subtracted from each other, times the integral from a to b of the function. Okay? So this is the height of the rectangle guaranteed by the mean value theorem. Okay? So this is the average height. The c that's involved is the x value where the average height occurs. So c equals the x value where the average height occurs. So again, in terms of physics, your c would be the time where your average velocity would occur. Okay, so things like that. This is a big thing in calculus. This mean value theorem, they'll ask 5 or 6 questions on each AP test about it. So this is a really good thing to make sure you understand. So let's take a look at the examples on the next page. Okay, and I think it's easier than most people think it is. So given this function x squared plus 1 on the interval from 0 to 2, so this is my a, this is my b, and it happens to be the problem on the previous page. They want us to find the average value of the function, okay? Then they want you to find the value of c. So what is the average height? What is the y value? And then at what x value does that occur at? Okay, so here we go. Okay, so I'm not sure what happened with the camera, but let's try that again. Okay, so given my function x squared plus 1 on this interval, I was going to solve this. So the average height of the function should equal 1 over b minus a times the integral from a to b of my function dx. Okay, so the average height of the function should equal, it's essentially the function, or the area divided by the width, right? So the average height should be the area divided by the width. So this is going to be 1/2 1/3 x cubed plus x from 0 to 2. Okay, if I plug in 2, that's 8/3 plus 2. If I plug in 0, that's going to cancel out, so I don't really care about it anyway. 8/3 plus 2, 2 is 6/3, so that's 14/3. So this is 14 over 6, or 7 over 3. So that tells me that the average height of my function is 7/3. Okay, so if you're talking about this in terms of a graph, and you don't need to write this down, I just thought I'd show you. So this is the parabola, right? We saw it on the last page. So if this is the 0 and this is 2, what this 7/3 represent is somewhere on this function, somewhere which is at 7/3, which is a little bigger than 2. So at 7/3, this value of c right here is the average height of this function. Okay, so it is the average height or the average velocity or whatever it is you're looking for. It is the average value, average y value on this function. Okay, so then the question they're asking you in part C, what value of c is guaranteed by the mean value theorem for integrals? All that means is, okay, so we know the average height is 7/3. Where does that happen in terms of x? Okay, well, if I know the y value is 7/3 and I know that the y value should be x squared plus 1, then this function is just x squared plus 1 equals 7/3, and then we just have to solve it. So x squared, subtract the 1, so that's what, 3/3, so 4/3. Take the square root of both sides, so x is 2 over the square root of 3. So the spot C where this average value happens is 2 over the square root of 3. And you don't have to rationalize, so that's it. That's all you have to do. Okay, so it's really not that difficult. It's just a matter of making sure you understand what's going on. Okay, so let's look at the second example. So we want the average height of the function, average value, right, of this function on this interval. Okay, so this should be pretty easy. So the average height or the average value of the function equals 1 over pi minus 0, the integral from 0 to pi of sine x dx. And then we just have to solve it. So the function, average height of the function should be 1 over pi times, the integral of sine is negative cosine from 0 to pi. So the average value or average height of the function is 1 over pi times, okay, if I plug in pi and I plug in 0, well, cosine at pi is negative 1, but it's negative 1, so this becomes positive 1. Make that plus. Cosine at 0 is 1, so this is 1 plus 1 times 1 over pi. Well, 1 plus 1 is 2 times 1 over pi, so the average height of my function is 2 over pi. Okay, so the average value of this function on the interval from 0 to pi is 2 over pi, okay? And now where does that happen? Well, that happens where sine x equals 2 over pi, okay? And you're not going to be able to solve this by hand, so this would have to be a calculator question, because remember, to solve this, you would need to do sine, like inverse sine. So on your calculator, you'd hit second sine of this equals x. And when you plug this piece into your calculator, you're going to get that x equals, where did I do that? 0.690. When you plug that into your calculator. So you're going to get this. So this is the spot at where an x equals 0.690 that the average height of 2 pi is reached. Okay, so hopefully that makes some sense. If not, I'll try and explain it a little bit better in class tomorrow when I get there. But hopefully that makes some sense to you. So the next thing is the second fundamental theorem of calculus that I feel like the workbook kind of makes more difficult than it actually is.